So let's say we want to, we're going to find the dimensions of the largest rectangle that can be inscribed. Not do it for me. In an isosceles triangle whose base is 8 inches and height is 5 inches. That's actually not height, but sorry. Whose other two sides are 5 inches. All right. Let me give everybody the. So if I was doing a problem like this, I would start by drawing a picture. Specifically, it's an isosceles triangle. I want to put the side that's the odd man out. I want it to be centered that way. So I'm thinking of my triangle looking like this. There's an 8-inch side, my 5-inch sides. Kind of like that. And the thing is, I really want to, well, actually, let's draw the rectangle first. So here's the rectangle that I'm inscribing in this thing. I want to maximize the area of that. So my base is my height. And the problem here is that to be able to do this, I really need to kind of like, it's not going to help me just to label this side's 8 and these sides is 5. I really need to put this on the coordinate axis system. So I'm going to specifically make it so that the origin is right there. And now with this base being 8, I know that this point on the x-axis is 4, 0. And with this height being 5, I know this point here is 0, 5. I meant to pick a different number there. Oh well. It's going to come out less than pretty. That's fine. So we are going to now, well, we want to maximize. That's a good question, actually. What do we want to maximize? We're trying to find the largest rectangle. We're trying to maximize what? Well, area. So typically they'll tell you, but if you're trying to maximize something or find the largest something, we usually mean the largest of its largest dimension. So if I was trying to maximize like a cone, we would say that we wanted the cone with the, or opposite. If I'm the largest cone, we say we want the cone with the most volume. Or if it's a two-dimensional shape, we want the thing with the most area. So let's see here. We want to maximize the area, which is going to be base times height. Now, here's the thing about inscribed type problems. When you have a shape inscribed in another shape, usually the corner where one shape touches the other is kind of important. Specifically, I want to label this corner. Well, I could label it the height, half the base and the height, but I'm going to pick kind of x and y just to make it easier. So I'm going to say this point here is x, y. So then my base is actually 2x, and my height is y. Does that make sense what I'm doing there? Sure, yeah. So all I'm doing is I'm saying, I'm going to call this point x, y. And the reason, if you look at my rectangle here, right, what I'm saying is that's the point 0, 0. Over here, I've gone over x. And over here, I've gone up y. So my height is definitely y is the height, but my base is twice x. So that's why I'm writing it that way. But still, we have our area as a function of two variables, and we want it to be a function of one variable so that we can take the derivative, find the critical values, et cetera, et cetera. So what's our constraint then? Well, our constraint is that that point needs to be on that line, right? You wouldn't want to draw a rectangle that was, say, not touching the triangle, because then you wouldn't be maximizing the area. And if I drew that rectangle, I could definitely make it bigger just by making it either taller or wider and still have it be inscribed. So definitely, if you're trying to maximize the area, you want it to be touching the triangle somehow, so that it's reaching its upper boundary of potential. So that point there needs to be on this line. And we can definitely find the equation of that line. So that line, well, the slope is, well, let's see, the slope is 5 minus 0 over 0 minus 4, which is negative 5/4. And the y-intercept is 5. So the equation is y equals negative 5/4 x plus 5. And that is what's going to go in for y right there. So now we can write the area equation as a function of x. And it's going to equal 2 times x times y, which is negative 5/4 x plus 5. And this is usually what we're doing when we're trying to optimize something, right? We typically have something we want to optimize. It's often a function of more than one variable. Then we have to use a constraint so that we can isolate one variable and plug it back into the other thing to get it as a function of one variable. Seem good so far? Okay. I would rather not use the product rule, so I'm going to multiply this out. It's going to be, let's see, 2x times negative 5/4 x is going to be negative 5/2 x squared, and 2x times 5 is 10x. And now if we take the derivative of negative 5/2 times 2x is going to be negative 5x, and the derivative of 10x is 10. If we set that equal to 0, we're going to get x equal to positive 2. Now, I don't know if they're going to ask you to check this when you take an exam, but typically at this point, we need to verify or check that that is actually giving us a maximum area, right? Every critical value doesn't necessarily give you a max or a min, right? But this could be a minimum, or it could be neither. It's probably a max, but we need to check. So how do we check? Well, we're going to do the first derivative test. So there's x equal to 2. Now, we need to be a little bit careful here. X, although x really could be anything as far as this area function is concerned, if you look back at your original picture, what's the biggest that x can really be? Well, it wouldn't make sense for x to be any larger than 4, right? Because then you'd be having a rectangle whose base was wider than the triangle it's inscribed in. So we should actually be stopping at 4. And similarly, it wouldn't make sense for x to be any less than 0. So one way you could do this is you could say, well, okay, the function, the derivative, if you plug something bigger than 2, like 3, the derivative is going to be negative. If you plug something between 0 and 2, like 1, the derivative is going to be positive. So the function's increasing, then decreasing, which means you have a maximum. So we definitely have a maximum at x equal to 2. Something else people do, though, with this, instead of using the first order test like this, they use the absolute max or absolute min test. They say, well, this particular function for area is defined on a closed interval. Right? If you look at when x equals 0, well, if x equals 0, what's the area of the rectangle going to be? It's going to be 0. And if x equals 4, what's the area of the rectangle going to be? Well, if x is 4, you've got a really, really wide and really, really not tall rectangle, right? Like the rectangle has no height. So what people often do with this kind of situation is say, well, the area when x is 0 is 4, the area when x is 4, sorry, the area when x is 0 is 0, the area when x is 4 is 0, and the area when x is 2 is going to be positive. If you plug in x equal to 2 for the area, you're going to get negative 5/2 plus 5, which is 5/2. So this one has to be the maximum value. That only works if the domain of your function, in this case, the area function, is a closed interval, and you can actually check the endpoints. Typically, this is the better way of doing this. So you have a maximum when x equals 2, and then we still need to find the other dimension. So we're going to get y equal to, let's see, y was negative 5/4 x plus 5, so it's negative 5/4 times 2 plus 5, which is going to be negative 5 halves plus 5, which is 5 halves. So the height, which is y, is going to be 5 halves or 2.5 inches. The base, which is 2x, is going to be 4 inches. So it's, be careful, right? The dimensions are x and y. The dimensions are 2x, which is the base, and y, which is the height. Questions about that? You can just say no, like just you. I mean, you guys also can ask questions on the Zoom. I know you might not be as engaged as if you're a person, but you are welcome to ask questions. All right, let's look at a similar but somewhat different example. Oh, nice. All right. So now we're going to instead, it always happens. I always write too hard on the paper. Let's go that way. Let's find the dimensions of the largest cylinder. Since it's three-dimensional, we mean has the most volume. Oh, sorry, thank you. It's the largest cylinder by volume that can be inscribed in a cone of radius 6 inches and height, sure, let's go 12 inches. Let's go 9 inches. So here's the thing about three-dimensional shapes. It's usually not super helpful to draw them three-dimensionally, meaning drawing a sphere, sorry, I said sphere, I said cone, I meant sphere is the next one. Drawing a cone with a cylinder in it is not super duper helpful. It's nice to draw pictures. And I know the radius, I'm going to call the radius of this R and the height of this H. But really, it's more helpful to draw the two-dimensional projection of this onto the XY plane. So instead of drawing a cone and a cylinder inside it, I'm going to draw a triangle and a rectangle inside it, kind of like I just drew before. So this is really going to be more like this. And as is typical, when I have a shape, I usually am trying to center it somehow on the XY coordinate system. So if it's a triangle, usually the base of it should sit on the x-axis with the middle of it at the origin. If it's a circle, usually you want the center of the circle at the origin, or if it's a semicircle, you want the center of the semicircle at the origin. Doesn't look perfect, that's all right. And this point here, well, since the triangle has a height of 9, that's going to be 0, 9. And since it has a radius of 6, that's going to be 6, 0. And then, I know this looks very lopsided here. That's my radius of my cone. That's my height of my cone. And this point on the line is, I've gone over R and up H. So we're trying to maximize the volume of the cylinder, which is going to be pi times R squared H. Right, that's the volume of your cylinder. And as is typical, right, the thing we're trying to maximize has two variables in it. So we need a constraint that equates one variable in terms of the other. So here our constraint is again that corner of your shape is on that line. So in this case, the line is, well, the slope is negative 9, 6, right? 9 minus 0 over 0 minus 6. The y-intercept is 9. So my equation is y equal to negative 9, 6, x plus 9. I could have reduced that fraction, but I didn't. Now, what I'm going to do here, which is slightly different than what I did before, is I'm actually going to, since my equation is in terms of R and H, I'm actually going to plug in R for X and H for Y. So that my constraint is going to be H equal to negative, I'm going to say 3/2 R plus 9. And I'm just doing that because my equation is already in terms of R and H. I could have instead said, right, R is X and H is Y and done it that way, but it doesn't really matter. So then we're going to rewrite our equation. What we want to maximize, we've got volume equal to pi times R squared times this, negative 3/2 R plus 9. And again, I'm not going to use the product rule if I don't have to, so I'm going to multiply this out. So I'm going to write volume equals pi times negative 3/2 R cubed plus 9R squared. I'm going to take the derivative of that. So V prime of R, if you prefer, is, let's see, bring down the 3, so it's negative 9/2 times R squared plus 18R. And set that equal to 0. And I'm going to factor out, I'm going to factor out at least an R. You might factor out a 9R. That seems not unreasonable here. So I factor out a 9R. I've got pi times 9R times, let's see, a negative 1/2 R plus 2. I might even factor out a negative 1/2 as well. To factor out a negative 1/2, I've got negative pi over 2 times 9R times R minus 4. So my critical points are R equal to 0. That's not going to be my answer, right? A radius of 0 is definitely not going to maximize the volume, or R equal to 4. I am always of the opinion that you should check to see it's actually what you want. So if we look at the number line here, well, again, the smallest R would be 0. And the biggest R would be 6. You could either do the thing where you say, well, look, James, I know that if I plug in 0 for the radius, I'm going to get 0 volume. And I know if I plug in 6 for the radius, I'm also going to get 0 volume. Because if the radius were 6, the height would be 0. And then you say, well, then 4 has to be maximum. Or you could actually do the thing where you check the number line and the derivative and say, okay, plug in 1, that's a negative times a positive times a negative, which is positive. Plug in 5, it's a negative times a positive, which is negative. So it is increasing, decreasing. Oh yeah, you've got a maximum of 4. Great. So then we need to find the other dimension. So we've got R equal to 4 inches, and the height is going to be negative 3/2 times 4 plus 9, which is negative 6 plus 9, which is 3 inches. Something that's kind of interesting that I've noticed over the years is that whenever you've got this previous triangle situation, you always end up getting that both the base and the height are kind of half the possible distance, right? Between 0 and 4, the base, well, I mean, the x value ended up being 2. And between 0 and 5, the height ended up being 5/2. And that's kind of because each dimension here counts as much, right? When you're finding the area, you're multiplying base times height. So the base and the height kind of are equally important. So that's what happens when there's nobody moving around the room. The lights go up, you have to walk around. But interestingly, in this other problem, where we're trying to maximize the volume of the cylinder, on the volume of the cylinder, the radius is much more important. Right? When you multiply that all, you're going to get radius times radius. And when you find the volume of the cylinder here, you're getting that the radius is 2/3 of its total possibility, right? 2/3 of 6 is 4, and the height is 1/3 of how much it could be. And that's because the radius is kind of twice as important as the height when we're calculating the volume, or twice as, there's a better word than important, twice as, I don't know, twice as effective, twice as impactful. The radius is twice as impactful as the height when calculating volume. So if you ever ask this kind of question, it's always going to be the case, as long as it's as long as this kind of setup, that the radius is 2/3 of the possible length it could be, and the height is 1/3 of the possible length it could be. Kind of neat. Now you would still need to show your work if this is a question on the test, but you at least have an idea like, oh yeah, I know the height's going to be 1/3 of whatever that total height is, and the rate's going to be 2/3 of whatever the radius is. Kind of nice. Let's do one more inscribing one because there's one more thing I kind of want to show you guys. So let's ask the question. Again, finding dimensions. Let's find the dimensions of the, sorry, you can't see the thing. Apologies. Of the largest cone, again, by volume, since it's a three-dimensional shape. Oh, you guys can't see me. I keep sorry about that. Not that it's like super important that you guys see me, but I am looking at you all the time. So I should be like, hey, I'm looking at you. Looking at all of you. Hopefully that's a little more like, okay, yeah. I was trying to look at myself looking at you, but I can't. So hopefully you can see me looking at you. You want to find the dimension of the largest cone by volume that can be inscribed in a sphere of radius 6 inches. And just like last time, it's not going to be super helpful to draw the three-dimensional shape, right? If I draw, like, here's my sphere, here's my cone inside it, right? That doesn't really let me label things very nicely. I mean, I know that the radius of the sphere is 6 inches. And here is the radius of the cone, which is not 6 inches. And here's the height of the cone. I guess it's technically possible that the answer could be that the radius of this cone was 6 inches right there. If the base of the cone was literally like this circle here, that would be a possibility, but we're not just going to assume 6 inches. The picture I really want to draw, though, instead of a sphere with a cone in it, is a circle with a triangle in it. And the nice thing about cones is that their projections are isosceles triangles, right? This side and this side should always be the same. And I'm going to put my coordinate axis system at the center of the circle. There's my origin. And actually, I might not have really needed that, but that's okay. It's still good to think about where the center of the circle is. So here's what we have. We have that this height is h, and here is my radius. And I'm trying to maximize the volume of the cone, which is 1/3 pi r squared h. So what I need to do here, just like I need to do every time, is I need to get a constraint by finding some equation relating those two variables. Now, it's not quite as easy as before. Right? There isn't like a nice point on a line like there was in the previous two examples. So what we need here, and this is kind of, this often comes up. Actually, another example where this comes, I'll come back to this in just a second. But another example where this comes up is when you're like trying to say maximize the area of a rectangle inscribed in a semicircle of radius 6 inches. In this kind of setup, here's your semicircle. Here is your rectangle. And the idea is that this point x comma y is on the semicircle. And you can either just know the equation of the semicircle, or what we typically do is we draw the segment connecting the center of the shape and the place where they touch. Often the place where the two things touch is kind of the most important point on there. And so then you can say, oh, well, if this is x, and this is y, and we know the radius of the circle is 6, then your equation is x squared plus y squared equals 6 squared. So often, if you're not sure what to do and you've got one shape inscribed in another, a good plan of attack is draw the segment that connects the center of the whole system to the point where the things touch each other. Because now, check this out. This is a right triangle. That side is R. This side is 6. And this side here, well, this whole length is 6 from here to here. And this whole length is h from here to here. And this length is 6. So this length here has to be h minus 6. And then we can use the Pythagorean theorem. Say, oh, r squared plus h minus 6 squared equals 6 squared. Oh, sorry. Yeah, please don't hesitate to ask. Yeah, apologies. Now, here's an interesting thing. In the previous problems, we didn't really talk about it, but in this one, right, in both of these, it was kind of obvious which thing we were going to solve for. Here, it didn't really matter. You could have solved for x or y, and it would have worked out fine. Here, it definitely made more sense to solve for h. Well, one, because it was already solved for, and two, it's easier to plug in for h than it is to plug in for r because we have to square r out. Now, here's an interesting thing. Either way, solving this for h or for r is going to be kind of gross. Solving it for r, we'd subtract that, take the square root of both sides. Solving for h, we'd subtract that, square root of both sides, and then add 6. So you can either get, now, you don't actually want to do this work, but I'll just point out, you can either get r squared equal to 6 squared minus h minus 6 squared, and then take the square root of both sides. We don't need a plus or minus because it's got to be positive, right? It doesn't make sense for the radius to be negative. Or you can solve for h and say h minus 6 squared equals 6 squared minus r squared. H minus 6 equals the square root of 6 squared minus r squared. And h equals 6 plus the square root of 6 squared minus r squared. What I want to point out is neither of these is the best thing to do. The best thing to do is to notice that, well, I don't just have an r in my equation, I have an r squared. And since I have an r squared here, what I can do is I can actually just solve for r squared. So the best thing to do in this situation is to say r squared equals 6 squared minus h minus 6 squared. And not do anything else to this other side. Leave the other side as r squared. You can simplify this right-hand side a little bit. Sure, yes, 1 second. So the way, actually, yeah. So the way I got the constraint was first by doing the thing that we often do in an inscribed situation, which is draw the segment that's connecting the center of your shape to the corner where the inscribed thing touches the circumscribing thing. So I wanted to draw the segment where the center touches the corner where they touch. And then I have a right triangle. I know the hypotenuse is 6 because that's just the radius of the sphere. I know that this base is r because that's the radius of the cone. And this part here, well, I know that this entire length from here to here is the height of the cone, which is h. This length here is 6. So this length here has to be h minus 6. And then I use the Pythagorean theorem to say that r squared plus h minus 6 squared equals 6 squared. That's how we got that. Hopefully that clarifies things a bit. Now we're going to simplify this just a tiny bit. R squared is going to be 36 minus h squared minus 12h plus 36. The 36 is canceled, and you get r squared equal to negative h squared plus 12h, or 12h minus h squared. And this is kind of great because now what we're going to do is we're going to plug that in to the thing we're trying to maximize. So check this out. We're going to maximize the volume equation is going to be 1/3 pi times r squared, which is 12h minus h squared times h. There's your volume. There is your r squared. I'm going to distribute the h. So we get volume equal to 1/3 pi times 12h squared minus h cubed. And then we're going to differentiate that. So the derivative is going to be 1/3 pi times 24h minus 3h squared I'm going to factor out a 3h. So I'm going to get pi, because the 3 will cancel the 1/3, h times 8 minus h. So I either get h equal to 0, which we know is not the right answer, or h equal to 8. Checking to make sure it's a maximum. You know that the smallest h could be is 0. The biggest h could be is what? A little bit bigger than that. Actually, twice as big as that. Right, because you could go the full height of the diameter of the sphere. So yeah, the biggest the height could be 12. Yeah. And then, yeah, 0 would be weird. If you pick something between 0 and 8, like 1, this derivative is definitely going to be positive. Something between 8 and 12, like 9, derivative would be negative. So yeah, it's a maximum. And then the height is 8. We know that the radius squared is going to be, I might factor this to make it a little bit easier. And if I factor out an h, it's h times 12 minus h. And then plugging in 8, I get 8 times 12 minus 8, which is 4. Which means the radius itself is going to be the square root of 8 times 4, which is the square root of 32, or 4 root 2. And that's how you would do this particular problem. Kind of neat. All right, questions about any of this so far? Welcome to Nutripol on Zoom. Again, if you guys have other things you want to see, let me know. I'm going to do a few more optimizations, but I do think we should start talking about Lubitel's rule, because if it hasn't come up yet in your class, it's certainly going to. I had one more example I really want to do. Let's see if I can find it. Let's see here. I got 2 more examples. So let's look at this example. Have we done this one before? Yeah. We did, okay. I couldn't remember if I did this class or the other class. So I thought that was. Let's say we have this. We want to construct. Yes, thank you. You always feel like I always feel like I should get there. Let me do that instead. We want to construct an open top box from a square piece of cardboard. (12 inches on each side). By cutting out a square from each corner, and bending up the sides. What size square should we cut off to maximize the volume? All right, so as is typical, we're going to draw a picture, because of course we're going to draw a picture. That's the only way I can really do these things. So here is my 12-inch by 12-inch piece of cardboard. And the idea is I'm cutting out a corner here, and here, and here, and here. And I'm going to take the remaining shape and fold up the sides. So I'm going to call the length of the corner I'm cutting out X. So this side here is going to be 12 minus 2x. as is this side here. And then the box I'm going to make is going to look like, well, so right, I'm kind of, this is going to be the base of my box. And these four sides are going to be the four sides of the box. So it's going to look like this. Where this length here is your 12 minus 2x, that's a 12 minus 2x, and the height of the box is just x. Well, great. That means we want to maximize the volume of this box, which is going to be x times 12 minus 2x times another 12 minus 2x. We don't even need a constraint. Right? Our function that we want to maximize is already a function of one variable. Awesome. So take the derivative. And yeah, I guess I would do it like that. I was considering multiplying it out, but I do think it's probably better just to use the product rule here. So my derivative is going to be 1 times 12 minus 2x squared plus x times the derivative of 12 minus 2x squared, which is 2 times 12 minus 2x to the first times negative 2. And we're going to simplify and set the equal to 0. Now, from each of these two pieces, what can I for sure factor out? I mean, I could factor out a 2, but there's a different answer that's going to be a little bit nicer. So this piece here, although you could factor out a 2 from inside here, there is a 12 minus 2x squared. And there's a 12 minus 2x over there. So what I really am going to do to make my life as easy as possible is factor out a 12 minus 2x. And if I do that, I'm left with, well, here I'm left with a 12 minus 2x to the first. And here I'm left with, well, I factored out the 12 minus 2x, so what am I left with? X times 2 times negative 2, which is a negative 4x squared. That feels a little dubious, I gotta say. Why? How am I getting x squared? I'm not, right? I'm imagining extra x in there. I am, right? I have x times 2 times negative 2. That's a negative 4x, not a negative 4x squared. So we've got 12 minus 2x times 12 minus 2x minus 4x, which is 12 minus 6x. We're setting that equal to 0. So we're either getting x equal to 6 or x equal to 2. So if x were 6, what would the length of each side be? Yeah. Right. Which means that's definitely not the answer, right? Because we don't want a box that has 0 volume. So when we're looking at the number line deal here, the least x could be a 0. That would give you a volume of 0. The most x could be a 6. Our critical value is 2. So again, what people often do here is they say that the volume at 0 is 0, the volume at 6 is 0, and the volume when x is 2 is positive, so that has to be a maximum. Or you can do the number line thing and say, okay, if I pick a number between 0 and 2, like 1, my derivative is definitely positive. Pick a number between 2 and 6, like 4, my derivative is definitely negative. So it's a maximum. The reason I'm subtracting 4x is because, so this is 1 times 12 minus 2x squared plus x times 2 times 12 minus 2x times negative 2. I factored out the 12 minus 2x. So I'm left with, so after I factor out 12 minus 2x, here I have a 12 minus 2x. I always say plus, right, because it's still plus. I factor out the 12 minus 2x here, but I'm left with an x times 2 times negative 2x, which is a minus 4x. So when you factor out, you still keep the addition or subtraction between the two things. And then 12 minus 2x plus negative 4x is 12 minus 6x. And that is the answer to the question, that x should equal 2 inches. That's going to be the cut that maximizes the volume of our box. All right, let's look at one more optimization problem. It's a little bit of a lengthy one, but it's okay. And then we'll take a break. Yeah, I don't know about this problem. So it's fine. It's worthwhile. So, yeah, we are on a boat, and we happen to be exactly 5 kilometers from shore. And we want to know, I don't know, I'm trying to like, what's the situation? So over here, there's a hospital, which is exactly 13 kilometers from where the closest point on shore is to us, to the hospital. And in our boat, we have an injured person. We want to get them to the hospital as quickly as possible. And so what we're going to do is we're say, well, I want to know what's the fastest way to get to the hospital, assuming we can row at, let me make up some numbers here, 5 kilometers per hour. And we can walk with the person at 4 kilometers per hour. Where should we row to so that it takes us the least amount of time to get there? Right, because it's probably, well, it might actually be fastest to row straight to shore and then walk for 13 kilometers. Or it might be fastest to actually row straight to the hospital. But it's often the case that it's going to be some sort of in-between place where we're going to be like, well, okay, we're going to do that. So let's actually calculate how long each of those are going to be before we start doing this problem. So this is a nice 5. I meant to make this 12, sorry. It's supposed to be 12 kilometers. It's a nice 5, 12, 13 triangle. So let's see, if we row straight to shore, well, we row at 5 kilometers per hour, it's 5 kilometers. So the time rowing is going to be the distance divided by the rate we row at. That's just going to be 1 hour, right? Obviously, if we row 5 kilometers per hour and it's 5 kilometers away, it's going to be 1 hour. And the time walking is going to be 12 kilometers divided by 4 kilometers per hour, which is going to be 3 hours. So a total of 4 hours if we row straight to shore and then walk the 12 kilometers. Or if we row straight to the hospital, well, that's a distance of 13 kilometers divided by 5 kilometers per hour. That's going to equal 13/5 of a kilometer of an hour, which is a little bit less than 3 hours. That's going to be 2.6 hours. That seems superior. I feel like I might have set this problem up in a way that where it comes. I feel like I might have gotten things switched around as far as like which one should be faster. But that's okay. We can still talk about how this problem works. So what if instead I say I'm going to row to here? Well, I need to label this x, and this distance here is 12 minus x. So the distance I'm actually going to row is going to be the square root of 25 plus x squared. So the time I spend rowing, or the total time I spend traveling, is going to be the time I row plus the time I walk. The row time is going to be the row distance divided by how fast I row at. And the time I walk is going to be the walk distance divided by how fast I walk. Okay, well, the distance we're going to row is this square root of 25 plus x squared divided by 5. And the distance we're going to walk is going to be this 12 minus x divided by 4. That's our function for how long it's going to take us to walk to get there from where we are on the boat. So now we're trying to minimize this time. So we're going to take the derivative, set it equal to 0, and see what happens. So taking the derivative, it's going to be a little bit ugly. It's going to be, so I'm thinking of this as, I might simplify this first. Let's write this as 1/5 times 25 plus x squared to the 1/2 power. And 12 over 4 is 3 minus 1/4 x. So then taking the derivative, we're going to get, let's see, 1/2 times 1/5 is 1/10 times 25 plus x squared to the negative 1/2 times the derivative of that, which is 2x, plus 0 minus 1/4. Set that equal to 0. Let's simplify this a bit. Cancel a 2 there and a 2 there. So I've got x over 5 times the square root of 25 plus x squared minus 1/4 equal to 0. This is definitely a situation where I would add the 1/4 over here and do some cross multiplying. So I'm going to say, okay, x over 5 square root of 25 plus x squared equals 1/4. So 4x equals 5 square root of 25 plus x squared. Square both sides. 16x squared equals 25 times 25 plus x squared. Multiply that, I guess. What's 25 times 25? 625. I'm a little worried though, because look what happens. I get 9x squared equal to negative 625. There's no critical values. Sometimes that happens. So what does that mean if we find no critical values? Well, it means that we should go back to what we already did and say, well, we saw before that if you walk straight to shore and then walks, or row straight to shore and then walks to the hospital, it's going to take 4 hours. And if we row straight to the hospital, it's going to take 2.6 hours. So clearly that is our answer here. So sometimes either you don't get a critical value or one of your endpoints is the best answer, is the answer that minimizes or maximizes the thing. All right, we'll take a quick break so I can use the restroom. We'll be back in a couple minutes, and then we'll talk about Lobitel's rule, unless there are other specific things people want to see. Before we get going with Lobitel's rule, I'll just put this up here. So here's kind of the beginning idea that we're going to talk about. You guys can take a look at that for a second while I go use the restroom to get more water. Yeah, we talked about the mean value theorem. We definitely talked quite a bit about it last class, though, so I will also encourage you to look at the lecture from last class if you haven't already seen it, because we definitely did talk about the mean value theorem there. Problem with the mean value theorem is there's not a lot to say about it other than kind of stating the theorem and then asking a couple specific types of questions. So we'll do a couple examples of the mean value theorem, and then we'll talk about Lubitel's rule. So that's not the kind of one. Mean value theorem. Here's the gist of it. It says if a function f of x is continuous on a closed interval a, b, and differentiable on the open interval from a to b, then there is a point C, or a value C, between A and B such that f prime of C is equal to f of B minus f of A over B minus A. Or in other words, there's a point where the slope of the tangent equals the slope of the secant line. Or the instantaneous rate of change is equal to the average rate of change. Graphically, kind of looks like this. We've got a function that maybe starts here. Let's just do it that way. We've got a function that goes from, say, A to B. What we're saying is there's at least one point between A and B where the slope of a tangent line would equal the slope of the secant line. So there's probably at least like 3 points here. There's probably a point right about there-ish. There's a point probably right about there-ish. There's a point right about there-ish. What the mean value theorem says is there's at least one point between A and B where the slope of the tangent line is equal to the slope of the line connecting your inputs. In practice, there's not a lot we can do with this. One of the typical types of questions is to ask to say for a function f of x equal to 2 over x on the interval from 1 to 10, find all values guaranteed by the mean value theorem. So what we're saying is, so my function looks kind of like this, 2 over x. And from the point, there's my point when x is 1. And here's my point when x is 10. 10 comma 2 over 10 is 1/5. There should be some point between 1 and 10 where the slope of the tangent line matches the slope of the secant line. So it should be somewhere like, I don't know, maybe right about there-ish. And they're asking us to find it. So we're going to try and find C so that f prime of C is equal to f of B minus f of A over B minus A. So in this case, let's see. Our derivative is going to be, well, that's 2 times x to the first. We're going to have -2 times x to the negative second. That's my derivative. And we want that to equal f of b, which is 1/5 minus f of a, which is 2 over 10 minus 1. So that's what we're, that's what we're trying to solve. Okay, so I'm going to rewrite this a little bit. I'm going to have negative 2 over x squared equal to, I'm going to multiply this by 5 over 5 to make it a little bit easier. That's going to be 1/5 minus 2 times 5 over 10 minus 1 times 5, just to make life simpler. So I've got negative 2 over x squared equal to 1 minus 10 over 9 times 5. Oh, but 1 minus 10 is negative 9. That's just going to be negative 1/5. So negative 2 over x squared equals negative 1/5. Great time to cross multiply. So I'm going to get on the left, negative 2 times negative 5 is going to be 10. On the right, x squared. So x is going to be plus or minus the square root of 3. Now, it's really important that our answer only includes values that are in the interval. So the only correct answer here would be c equal to positive root 3. C equal to negative root 3 would be a point where the slope was the same. So if you graph this whole thing, here's 2 over x, kind of looks like this, kind of looks like that. There is a point, here at root 3, and over here at negative root 3, where the slopes of the tangents are the same. But we only want this one because that's the only one guaranteed by the mean value theorem that happens to be between 1 and 10. This one over here at negative root 3 is definitely not between 1 and 10, so we don't include it. I multiplied it by 5 to make it easier to deal with. I mean, I could have done the subtraction, right? I could have said, instead of multiplying this by 5 over 5, I could have said, well, okay, 1/5 minus 10/5. I could have made that. I just don't like fractions and fractions, so I was trying to get rid of the fractions as quickly as possible. But I could have said that's negative 9/5 over 9. And then the 9's cancel, and you do get negative 1/5. Either way is fine. I was just trying to do it the way that seemed the easiest. Other questions about that? So the mean value theorem is kind of most of what there is to it. It definitely gets used when proving a lot of other things, especially when you take 21B. Sure, so the way we got negative 2x in a second is our original function was 2 over x, which is 2 times x to the negative first. And so when I take the derivative of that, I brought the power down, and I got negative 2 times x to the negative 1 minus 1, which is negative second. So that negative 2x to the negative second, that's just the derivative of my function. F of x is 2 times x to the negative first. That's where that's coming from. Other questions? How did I get square root of 3? So, oh, yeah, that's a really good question. How did I get square root of 3? And yeah, that's a really good question. Because I was wrong. Yeah, good call. I don't know how I got square root of 3 when it should have been square root of 10. I think my brain must have been thinking that the square root of 10 is close to 3. Sorry about that. That seems like a very glaring mistake there. Where we should have gotten x equal to plus or minus the square root of 10. And then our actual answer would have been c equal to the square root of 10. Sorry about that. So these should have been. Yeah, that's real good there. So yeah, the actual answer is the square root of 10, not the square root of 3. Very, very good point there. Other questions or observations of mistakes I might have made? I don't think there are any mistakes I made, but there could be. All right. Sure, we can do one more. So we want to find all values of C, guaranteed by the mean value theorem. For f of x equal to 3x squared minus, sorry, oops, that's getting ahead of myself there. What for f of x equals to x cubed minus 4x squared plus 5x minus 7 on the interval from, let's go -2 to 3. All right, this might not be pretty. Let's make that interval less ugly. Let's go 0 to 3. All right, so we're trying to solve f prime of C equal to f of B minus f of A over B minus A. And we know there has to be a solution because our function is continuous and differentiable on the closed interval. Really, this function we know is continuous and differentiable everywhere because it's a polynomial. So I'm going to deal with this right-hand side first. So f of B minus f of A, that's going to be f of 3 minus f of 0 over 3 minus 0, which is going to be, let's see, so f of 3 is 27 minus 4 times 9 plus 5 times 3 minus 7 minus f of 0 is going to be 0 minus 0 plus 0 minus 7 all over 3. Let's see what we've got here. We've got 27 minus 16 is -9 plus 15 is 6. Minus 7 plus 7 doesn't, those cancel out. So we get 6 over 3, which is 2. Great. Now we have to set the derivative, which is f prime of x is going to be 3x squared minus 8x plus 5 equal to 2. And there should be a solution. So I'm going to subtract 2. 3x squared minus 8x plus 3 equal to 0. And I could try to factor that, but it might not factor. And I don't really want to waste my time trying to factor something that doesn't factor. So what I would probably do is jump straight to the quadratic formula. So my solutions are going to be x equal to -b, so +8, plus or minus the square root of b squared, so 64, minus 4 times a times c, all over 2 times a. So my answers are 8 plus or minus the square root of 64 minus 4 times 3 times 3 is 36. All over 6. That's going to be 8 plus or minus the square root of 64 minus 36 is going to be 28. All over 6. So I've got, well, that's what I've got. So let me see here. So the question is, which of these or both is which of these two answers is actually in my interval, or are they both in the interval? We know for sure at least one of them has to be. So is 8 minus the square root of 28 divided by 6 between 0 and 3? I think so, right? Because 8 minus the square root of 28 is certainly bigger than 0. And 8 minus the square root of 28 divided by 6, I'm pretty sure is definitely less than 3 because 8 over 6 is less than 3 and I'm making it smaller. So this one is certainly between 0 and 3. What about 8 plus the square root of 28 all over 6? Well, it's certainly bigger than 0. So if I didn't have a calculator handy, I know that the square root of 28 is less than what? What's the next biggest square root that's easy to do? Right, and square root of 36 is 6. So that's less than 8 plus 6 over 6, which is 14 over 6, which is definitely less than 3. So in this case, both of my solutions are actually values that are guaranteed by the mean value theorem. So both 8 minus the square root of 28 over 6 and 8 plus the square root of 28 over 6 are guaranteed, or values guaranteed by the mean value theorem. So sometimes all the answers you get are in the interval that you started in. Sometimes they're not. All right. Let's go ahead and talk about Lubitel's rule. And there's this little picture that I did not draw, someone else did, but I think it's worth looking at just to kind of help us believe a little bit why Lubitel's rule is true. So we're not going to actually prove it. It's kind of a giant pain in the butt to prove. But here's the idea. Lubitel's rule says that if the limit as x approaches a of f of x over g of x is equal to either a 0 over 0 or an infinity over infinity, has to be one of those two types. You cannot use it any other time. Then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x, provided one, that f and g are both differentiable, and two, that this limit actually exists. So the limit of a quotient is equal to the limit of the derivative of the top over the derivative of the bottom, as long as it's a 0 over 0 or infinity over infinity. Why is this true? Well, this isn't so much a proof as just kind of an explanation. Let's imagine we had two cars traveling, and A of t is the distance of car A, and A prime of t is the velocity of car A. And car B has a distance of B of t and a velocity of B prime of t. So suppose both cars travel for an infinite amount of time, but car A travels twice as far as car B. Okay, I mean, that seems weird, but all right. So if car A travels twice as far as car B, then the limit as t goes to infinity of A over B will be 2, because A is twice as much as B. Seem okay? Okay. But what does this mean about the car's velocities in comparison? Well, car A's velocity compared to car B's, car A must have been traveling twice as fast as you keep going forever and ever and ever, right? If you've covered twice the infinite distance, essentially you're going twice as fast the whole time. So the limit as t goes to infinity of the speed of car A over the speed of car B also has to be 2. Because if you travel infinitely twice as far as someone else, you were going for an infinite amount of time twice as fast as they were. Otherwise, your distance couldn't be twice as much as their distance. I know it's not like super precise what we're saying here, but it's kind of just giving us the idea that, oh yeah, if these two things have a limit that has this particular ratio, then these two things have a limit where their derivatives have that same particular ratio. All right, well, let's look at some examples. So here's a very kind of common example. I want to find the limit as x goes to infinity of x squared over e to the x. Well, that's an infinity over infinity type. Right, the top is definitely going to infinity, the bottom is going to infinity. So we can use L'Hopital's rule. Now, when I use L'Hopital's rule, I typically write an equal sign with an L apostrophe H over it to let whoever is grading my work know that I'm using L'Hopital's rule there. Not explicitly required, but it's a good idea. It's always good to help out the people who are grading your work. You want them to know that you want them to know that you know what you're doing. So we still have to write the limit because we're still taking the limit. The derivative of x squared is 2x. The derivative of e to the x is e to the x. This is still an infinity over infinity type. If that's the case, we use L'Hopital's rule again. So when you use L'Hopital's rule again, I get the limit as x goes to infinity of the derivative of 2x is 2. The derivative of e to the x is e to the x. And now this is no longer a L'Hopital's rule problem because it's not infinity over infinity. This is a finite number over infinity, which goes to 0. So our answer here is 0. And that's actually true regardless of the power of x. If someone asked you, and I saw this on someone's homework a while ago, what the limit is x goes to infinity of like x to the 200th power over e to the x is. Well, every time you use a L'Hopital's rule step here, you're going to lose a power on the x. Right? My first step would be the limit as x goes to infinity of derivative of the top is 200 times x to the 199 over e to the x. Every time you take the derivative, the power of x is going to be 1 less. And every time you use L'Hopital's rule, the power of x is going to be 1 less. And the e to the x is just going to stay the same. So after like 200 times, we're going to end up with the limit as x goes to infinity of 200 times 199 times 198 all the way down to like 1 all over e to the x. And that top part, although it's a big number, is not infinity. It's a big finite number. The denominator is getting infinitely large, and a finite thing divided into infinite number of pieces is going to be very small. Which is why we typically say that exponential functions always outpace polynomial functions. Or eventually will grow much, much, much larger than any polynomial function. Can L'Hopital's rule be used for any kind of limits? No, it's only so, well, no, it can be, yes. So yes, it can be used for limits as x approaches anything. What has to be true about a L'Hopital's rule type of, what has to be true to be able to use L'Hopital's rule is that the limit has to be a fraction, and it has to be a 0 over 0 or infinity over infinity type. But it doesn't mean that, but we do not have to have that x is going to infinity itself. So let's look at, and we'll definitely see some examples where x is not going to infinity. Just not quite yet. So look at this next example. Here's an example that you should already know the answer to almost as soon as I'm done writing it. Limit as x goes to infinity of 6x squared plus 5x plus 4 over 2x squared minus 3x plus 1. Everybody on Zoom should be able to chat me the answer. It's literally 1 digit. I would like everybody to please tell me the answer. I would like you to show me the answer on your fingers if you think you know it. It's okay if you don't. Oh, it's a little bit less than that. I saw one person on Zoom. So we're not subtracting, we're dividing. At least I think you were subtracting. You're not wrong. That's not the way I would have written it, but yes, that's totally correct. Yes, yes, also yes. So the answer here, the old way of doing it would have been, well, the really old way of doing this, we're going to divide everything by x squared, and get the limit as x goes to infinity of 6 plus 5 over x plus 4 over x squared over 2 minus 3 over x plus 1 over x squared. And then each of these things are being divided by x or x to the power are going to go to 0. So what are we left with? 6 divided by 2, which is 3. Or we could use L'Hopital's rule. This is definitely an infinity on top and infinity on the bottom, right? Both the numerator and the denominator are infinitely large. So if we use L'Hopital's rule, we get the limit as x goes to infinity of 12x plus 5 over 4x minus 3. And if we use L'Hopital's rule again, because it's still an infinity over infinity type, the limit as x goes to infinity of 12 over 4. That's just a constant, and the limit of a constant is just the constant. So that's going to be 12 over 4, which is 3. That's not exactly correct. So a couple things. So the question is L'Hopital's rule just deriving until either the numerator or denominator becomes a constant? That's often true, but not always true. Sometimes you get something where you can then cancel x's out, or something simplifies in another way. But yes, or you just get something where when you plug in whatever x is going to, it doesn't end up being 0 over 0 or infinity over infinity. The other thing is, I just want to clarify, we're not differentiating technically, we are differentiating the top and the bottom, right? We're not using the quotient rule or anything else like that. We're just saying root of the top over the root of the bottom. Let's look at some more examples. So let's do the limit as x goes to infinity of the square root of x divided by the natural log of x. which definitely is an infinity over infinity type. Right here are the graphs. Here's the square root of x, so it's kind of like that. Here's the natural log of x, does this kind of deal. And it's not really immediately clear which one is getting bigger or faster. Right? Maybe they're growing at the same rate. Maybe they eventually cross. Well, let's use L'Hopital's rule. This is definitely infinity over infinity. So using L'Hopital, we're going to get the limit as x goes to infinity of, let's see, the derivative of the square root of x. That's x to the 1/2. That's what that's equal to. So the derivative is going to be 1/2 times x to the negative 1/2. And the derivative of natural log of x is 1 over x. I'm going to write this in a slightly misleading way for just a second. If we wrote this as 1 over 2 root x all over 1 over x, we might convince ourselves that we should use L'Hopital's rule again. Because what we have here is a 0 over 0 type. Right, the denominator 1 over x is definitely going to 0 as x is infinitely large. And the numerator 1 over 2 root x is also going to 0 as x gets infinitely large. But whenever you're using L'Hopital's rule, before you use L'Hopital's rule again, it's usually a good idea to try and simplify your expression if it makes sense to you. And we can definitely simplify this. I'm going to write this as the limit as x goes to infinity of 1 over 2 times the square root of x times x over 1. And then x over the square root of x is just the square root of x. So this is equal to the limit as x goes to infinity of x over the square root of x over 2. But then as x goes to infinity, the square root of x goes to infinity. Infinity divided by 2 is still infinity. So we get infinity. So here's an example, right, where we didn't keep using L'Hopital's rule until we got a constant somewhere. We used L'Hopital's rule once. We didn't get a constant on top or the bottom, but then we simplified and we're able to take the limit. So you're not always going to keep using it until you get a constant somewhere. Other questions about this before we do some more examples? Also, as far as functions are concerned, right, what this tells me, and this is something you should really be thinking about, is whenever you're looking at this kind of thing, if your limit is 0, it means the numerator is much smaller than the denominator, right? The numerator is growing more slowly than the denominator. If your limit's infinity, it means the numerator is growing much faster than the denominator. So here, when I look at this result, what it means to me is that the square root of x grows much, much, much faster than the natural log of x. Or maybe you would say it as the natural log of x grows much, much slower than the square root of x. So if you were to grab a calculator and like take the square root of a million versus the natural log of a million, the square root of a million would be much larger than the natural log of a million. Now I'm curious, what is the natural log of a million? I know the square root of a million is 1,000. And the natural log of a million, let's find out. I have to do the thing. Come on, phone. I hate that you can't get the big calculator without opening your phone up. It's terrible. Yeah, sure. Okay. Oops, that's fine. Give me the calculator. Let's see. So the square root of a million is 1,000, and the natural log of a million is the natural log of a million is 13. So quite a big difference, right? Natural log of a million is about 13, whereas the square root of a million is 1,000. So clearly the square root function is growing much, much faster than the natural log function. Kind of neat, kind of worthwhile. Let's look at some more examples that don't involve limits as x goes to infinity. Let's look at the limit as x approaches 2 of x squared plus 3x minus 10 over x squared minus 4. Now, before we just start throwing L'Hopital's rule at every problem, and I should say, you can only use L'Hopital's rule if you're doing a limit, right? It doesn't make sense if you're talking about other things. But before I even try using L'Hopital's rule here, I need to check that I actually can. is this actually a 0 over 0 type? Oh, the lights went out. Oh my God. Yeah. So is this a 0 over 0 type? Yeah. If you plug in 2, you get 4 plus 6 minus 10 over 4 minus 4. Oh, yeah. That's 0 over 0. Back in the day, we might have done this by factoring. You can totally factor the top and say, well, and the bottom, and say it's x plus 5 times x minus 2 over x plus 2 times x minus 2, and cancel the x minus 2s, and plug in 2 and get 7 over 4. But you can also use L'Hopital's rule. Using L'Hopital's rule, you get the limit as x goes to 2 of the derivative of the top is 2x plus 3. The derivative of the bottom is 2x. Again, to kind of respond to the question from before, notice I didn't get a constant at the top or the bottom, but I'm not going to use L'Hopital's rule anymore because I can't. If I plug in 2 here, I don't get 0 over 0. So typically, when you're using L'Hopital's rule, every time after you use L'Hopital's rule, simplify if you can, and then try plugging it in. If you get a number, great, you're done. If you get 0 over 0 or infinity over infinity, use L'Hopital's rule again. So here I get 2 times 2 plus 3 over 2 times 2, which is exactly the same thing I got above. So L'Hopital's rule works. It's a pretty great tool. So I can't use L'Hopital's rule here again because we can only use L'Hopital's rule if it's a 0 over 0 type or an infinity over infinity type. But when I'm plugging in 2 here, it's not a 0 over 0 type anymore. It's a 7 over 4, which is my answer. So we can only use L'Hopital's rule for those indeterminate forms, 0 over 0 or infinity over infinity. Like this very well-known example that you've seen before. The limit as x goes to 0 of sine of x over x. We definitely talked about before how this limit's equal to 1. There's a very kind of nice, somewhat complicated geometric proof of it. But now we can just use L'Hopital's rule and be like, okay, well, it's definitely a 0 over 0 type because if you plug in 0 for x, you get sine of 0, which is 0 over 0. Using L'Hopital's rule, the derivative of sine of x is cosine of x. The derivative of x is 1. We can't use L'Hopital's rule again because it's no longer a 0 over 0 or infinity over infinity type. So then we just plug in and we get cosine of 0 over 1, which is 1 over 1, which is 1. Let's try another one. About the limit as x goes to 0 of sine of x minus x over x cubed. All right. So I really can't stress enough. Don't just throw L'Hopital's rule at every limit you see. 1, you have to make sure you can use it. 2, sometimes even when you can use it, you shouldn't. There are 2 specific examples I will show you where it is terrible or impossible to get there using L'Hopital's rule. This one is not either of those cases. If you plug in 0 here, it's definitely 0 minus 0 over 0. So we use L'Hopital's rule. And you get the limit as x goes to 0 of derivative of sine is cosine, derivative of x is 1, derivative of 3x, x cubed is 3x squared. Now this one, if I try plugging in 0, I get 1 minus 1 over 0, which is another 0 over 0 form. So now I can and should use L'Hopital's rule again. So using it again, I get the limit as x goes to 0 of derivative of cosine is negative sine. Derivative of 1 is 0. Derivative of 3x squared is 6x. Still 0 over 0. And use L'Hopital's rule again. Derivative of negative sine is negative cosine x. Derivative of 6x is 6. And I get, finally, plugging in 0, negative cosine of 0 over 6, which is negative 1/6. So sometimes you have to use L'Hopital's rule a few times. Yeah. A couple examples where using L'Hopital's rule is garbage. So here's an example where you can, but you shouldn't. The limit as x goes to 0 of sine of, let's just make this real awful, x cubed over 2x cubed. You could totally use L'Hopital's rule here 3 times. Right, this is 0 over 0 type. Let's see what the first step looks like if we use L'Hopital's rule. The limit as x goes to 0. Derivative sine of x cubed is cosine of x cubed times 3x squared. And the derivative of 2x cubed is 6x squared. Oh, actually, okay, fine. This one isn't as bad as I thought it was. I didn't make it quite as terrible as I meant to. This one's fine to use L'Hopital's rule for because things work out nicely. Didn't make it awful. How did I make? I'm trying to remember how I make this one more awful. This one, so this one's fine. Let me show you the one where it is going to be terrible. Here you can cancel out the x squareds, plug in 0, and you get cosine of 0 times 3 over 6, which is just 1/2. Here's the problem I meant to ask. The limit as x goes to 0 of sine cubed of x all over, let's just make it even easier, x cubed. So this problem, if we rewrite it so it's easier to differentiate the top and the bottom, I have sine of x quantity cubed over x cubed. And I'm going to show you L'Hopital's rule, and I'm going to tell you how awful it is. So using L'Hopital's rule the first time, we get the limit as x goes to 0 of, so the derivative sine of x cubed is 3 times my stuff squared times the derivative of my stuff, which is cosine x, all over 3x squared. You can totally cancel this 3 and this 3, but it's still a 0 over 0 type. So let's do L'Hopital's rule again. Now doing it again is where things start to get pretty gross. Because doing it again, the derivative of the bottom is 2x. The derivative of the top, I'm going to have to use the product rule. So the derivative of sine of x squared is 2 times my stuff to the first times the derivative of my stuff times the other piece. Right, so there's, if this is my f and this is my g, there's my f prime, there's my g, and then I need f, which is sine of x squared times g prime, which is going to be negative sine of x. It's looking gross, and more importantly, when you try to plug in 0, you get 0 plus 0 over 0, which is still 0 over 0. Okay, I'm going to do the third step, which I'm going to regret, but I'm going to do it all for you guys just so you can see how terrible it is. Here's what we've got. We've got 2 times sine of x times cosine squared of x minus sine cubed of x all over 2x. Using L'Hopital's rule, okay, I'm going to get the limit as x goes to 0. The denominator is going to be 2. And then on top, so I have to use the product rule here. So the derivative of 2 sine x is 2 cosine x times cosine squared x plus 2 sine x. And the derivative of 2 cosine x is 2 times cosine x to the first times the derivative of cosine, which is negative sine. And then the derivative of sine of x cubed is 3 times sine x squared times cosine x. Okay, we're almost done. Now we just have to plug in 0. Here's a nice thing to remember. Cosine of 0 is 1. Sine of 0 is 0. So I'm going to get 2 times 1 squared plus 2 times 0 times it doesn't matter minus 3 times 0 times 1 all over 2. This part's 0. This part's 0. You're left with 2 over 2, which is 1. Wow, that was a lot of work that we didn't need to do, because what we should have done, we should have said, okay, well, if I'm taking the limit as x goes to 0 of sine cubed x over x cubed, actually write that as the limit as x goes to 0 of sine of x over x times sine of x over x times sine of x over x, and just use the fact that each of those limits is 1. So typically when if someone asks you a question like this, they do not want you to do all this. They want you to recognize that, oh, I can break it up like this and say that's just going to be 1 times 1 times 1, which is 1. Definitely the way you should do a problem like this, right? This other stuff we did here is terrible. No one wants to do that. Okay. So to use Lobitel's rule, you have to have 0 over 0 or infinity over infinity. But sometimes there are other indeterminate forms that we need to manipulate to be able to look like that. For example, I want to find the limit as x goes to 0 from the right of x times natural log of x. Well, x is going to 0, natural log of 0 is going to negative infinity. This is a 0 times negative infinity type. And unfortunately, it's indeterminate, right? 0 times infinity could be anything. It could be 0. It could be infinity. It could be somewhere in between. What I want to point out here is that it's not actually 0 times infinity, right? Because 0 times a number would be 0. But what we have here is a number that's very, very small, right? That's getting closer and closer to 0, times a number that's very, very negatively large. So you have a very, very small number times a very, very large number. It's hard to know where you end up. Sometimes the smallness overpowers the largeness. Sometimes the largest overpowers the smallness. Sometimes there's a balance in between. In either case, you have to use L'Hopital's rule, but before we can use L'Hopital's rule, you have to write it as a fraction. So typically, you want to make it as easy to deal with as possible. So I'm going to write this as the natural log of x divided by 1 over x. So that now I have a fraction, and the numerator is going to negative infinity, and the denominator is going to positive infinity. And that's an infinity over infinity type. It's okay that the infinities have different signs. We don't need them to be the same. You just have to have either 0 over 0 or infinity over infinity to use L'Hopital's rule. So in this case, we're going to get, using L'Hopital's rule, the limit as x goes to 0 from the right of the derivative of the natural log of x is 1 over x. The derivative of 1 over x is negative 1 over x squared. And now we shouldn't use L'Hopital's rule again, right? It is an infinity over negative infinity type. I'm going to simplify. That's 1 over x times x squared over negative 1. I can cancel an x here and an x here and have the limit as x goes to 0 from the right of x over negative 1, which is just negative x. And if you plug in 0, you get 0. So when you have one of these other indeterminate forms, the idea is that you want to make it look like a fraction that's a 0 over 0 or infinity over infinity. Let's see here. What's another good example? I had one that I thought I wanted to do. Oh. Sorry, it's 1 second. My calf is kind of like. Okay. So let's look at the limit as x goes to infinity of x squared times sine of 1 over x squared, which is definitely an infinity times 0 type. X squared is going to infinity, sine of 1 over x squared is going to sine of 0, which is 0. So you have choices, but you almost always want to choose the simpler thing to go in the denominator, right? You could write this as the limit as x goes to infinity of x squared over 1 over sine of 1 over x squared. That is not the choice you want to make. Because derivative of the top is easy, derivative of the bottom is, that's cosecant of 1 over x squared. I don't want to take the derivative of cosecant of 1 over x squared. I would much rather do the limit as x goes to infinity of sine of 1 over x squared over 1 over x squared. That's going to be much easier to deal with. It's still not great, but it's fine. So using Lubitel's rule, we get the limit as x goes to infinity. The derivative of sine of some stuff is cosine of the stuff times, what's the derivative of 1 over x squared? Well, that's x to the minus second. And the derivative is minus 2 times x to the minus third, or minus 2 over x cubed. And on the bottom, we're again taking the derivative of 1 over x squared, which is minus 2 over x cubed. And look what happens. Those exactly cancel out. So we're left with the limit as x goes to infinity of cosine of 1 over x squared. 1 over x squared goes to 0, and we get cosine of 0, which is 1. So in this case, the infinity times the 0 has this kind of balancing, where this really, really large number times this really, really small number kind of balance out and come to a value that's close to 1.